Now we have to be a little careful with the inner product. So properties of inner product, we have to say xy equal to yx star. This is partly imposed so that the positive definiteness works. Okay, so if you have xx, it will be its own complex conjugate, so it will remain positive and so on. The second thing is therefore that if I put ax plus by comma w, it will come out a star x comma w plus b star y comma w. So in the second slot, the property will look exactly like this. Actually the property is exactly same, but if you put it in the second slot, but because when you flip it you get a star, that means if you had done it in the first slot, then you have to star the coefficients when you pull them out. And of course the third property remains the same. And the good news is that the Hilbert space of quantum mechanics obeys all of these. If you want to know why it is called Hilbert space, after all it's some complex linear space, right? You have to read the notes. It has to do with the infinite dimensionality and the fact that you eventually have to use the continuum to define plane waves. You have to define e raised to ik dot x, where you label the k is the parameter, is the wave number, but k takes all the possible continuous values. So to allow representing a free particle, you have to include all those kind of basis states as possible vectors, and there are subtleties that arise because of that. It's the same as the problem of Fourier series versus Fourier transform. Fourier transform is a more complicated thing than Fourier series, but you need not worry about it right now. If you want to read, there are discussions of why it is called Hilbert space, but it is essentially a complex vector space with a continuum number of vectors in it. The dimensionality may be finite, but in the sense that it may be in only one dimension or 2 dimension or so on, but it is an infinite dimensional vector space as a vector space. And more complicated things happen when you go to quantized fields, like in condensed matter physics and so on. There you have to consider, in fact, higher orders of infinities. Now coming back to this, we come back to our classical groups and we define orthogonal sets, orthogonal group. I wrote that too soon. There is ON and there is SON, and this is what I will discuss now. So essentially what we say is the matrix is O such that OX comma OY remains same as X comma Y. The inner product is preserved by multiplication of all vectors by O. The inner product is preserved. So preserves this IP. Or we call it the invariance group. Okay. In matrix notation, we would have the inner product has to be written as X transpose Y. We said that our matrix are our carrier space are column vectors, right? So the usual way of writing out the inner product is to take X transpose Y, and then we can see what we need is X transpose O transpose, because transpose of, I should have written that first, okay, but you know, you are grown up people. So therefore the property required is O transpose O equal to identity matrix. So that is the defining property of orthogonal group, and this group is called ON, the set of all such matrices it's obviously a subgroup of the GL and R, because when you take a general linear matrix which has an inverse but then restrict it to satisfy this O transpose O condition, it's a subgroup of the GL and R. And then in physics, we have to worry about one more thing. This O transpose O can also have matrices that will flip the axes, mirror reflect the axes. So first we write out, so further specialization. Note O transpose O equal to identity implies that determinant of O squared equal to 1, right, because determinant of O transpose O, there is a theorem of matrix algebra that this says that this is same as det O transpose times det O, and determinant of O transpose is same as determinant of O. Right. Right, determinant of AB is same as the determinant of product is product of the determinants, and further the determinant of transpose remains the same as the determinant of the original matrix. So det O transpose O is same as det O squared, and on the right hand side determinant of identity matrix is 1. So we will get det O squared equal to 1. This means that O can be plus or minus 1. Now if we take SO3, so if we take O3, matrix 1 1 minus 1 also belongs to it. But this is not a proper rotation, you have to flip the z axis. So this cannot be obtained by rotations that can be continuously reduced to identity. Okay, you cannot get this by any rotation of the xyz axis that can slowly be transformed back to identity. So this involves mirror reflection in xy plane and cannot be obtained by rotation. In other words, it cannot be obtained as a continuous variation of the identity matrix. So sometimes we call this improper rotation. Okay, it's not a, it is like a rotation but not actually a rotation, so we call it improper rotation. Is it safe to write here? To avoid, if you want to avoid improper rotation, sometimes you want to include mirror reflections, not a problem. But if you want to avoid mirror reflections, then you call it, then you put a further restrictions. The determinant O should be +1. Now we can see that this det O equal to +1 will be a subgroup of the ON. So this is called SON. Next, let us look at the complex groups. So we have stopped writing. For GL we said comma R, comma C. Here we don't, because by context it is always clear orthogonal groups are real groups and the unitary groups are automatically complex groups. So here it is a similar thing. It is leaving the complex inner product invariant. Again in matrix notation, we need x dagger, u dagger, u y equal to x dagger y, because the inner product in the matrix case will be equal to x dagger y. So this means that u dagger u equal to 1. Identity matrix. What this means in the complex case on the determinant, you will get complex conjugate of the determinant. So this is modulus of mod det u mod square. And this is set equal to 1. So this means that determinant u is some e raised to I theta. It is a phase, so its mod square should come out 1. So this is a much bigger ambiguity than in the orthogonal case, where you just got plus or minus 1, but here the determinant can lie on the unit circle. To restrict this, demand that determinant u equal to 1, i.e. theta necessarily equal to 0. This is then called special unitary group. In quantum mechanics, we actually have this, the only thing that we need for norm of wave function to remain the same is that they have to be unitary. So in quantum mechanics, okay, so we have to backtrack a little bit. What is the significance of these GL and R in geometric sense, or specifically of, let us say, the SON and UN, ON, SON, UN, SUN? What do these things do? What they really do is carry out a change of basis. So we said that the matrices act on various vectors, x goes to OX, x goes to UX. Think now x to be one of the basis vectors, okay, one of the unit vectors. Then all that we are saying is that we have rotated all the unit vectors the same way by this transformation u. So it amounts to just change of basis. It is this operation. In fact, even the general linear transformation is essentially a change of basis, but it also allows stretching the basis. It doesn't leave the magnitude 1. Whereas the orthogonal, so we can write this down. I want to do two things before we close. One is this and the other is the slightly algebraic notation. So maybe we do the algebraic notation first and then we come to this. Algebraic version of preservation of metric. Of the inner product, I am sorry. Note that for equal to x transpose y is same as x transpose identity times y. This is what it actually means. We want to think of the inner product a little bit more generally. The inner product is actually a matrix by itself. Okay. This is the Pythagorean choice. Well, and effectively Cartesian. We can more generally define any, so a generalization due to Gauss. Any matrix G such that x, y defined by x transpose G y. You insert this matrix G, but it should obey all the IP requirements, that's all. You don't say it is the identity matrix. You can put any matrix that you like. So typically it will turn out it has to be a symmetric matrix, that's all. Okay. So typically all symmetric matrices. So this is the generalization due to Gauss, and he calls it the metric tensor. Why it is tensor and all is a different story. But what we want to point out is that in fact the inner product, all it needs is some matrix G which is symmetric and which is such that x transpose Gx will remain positive definite. So those requirements is all it needs. Typically all symmetric matrices will satisfy this, and if you want ultimately you can make them determinant 1 symmetric matrices. So we can now think of this as preserving the Pythagorean metric 1. Okay. So this can also be written as O transpose O equal to 1 can also be written as O transpose G O. In Pythagorean notation or in Pythagorean choice, it becomes O transpose O equal to 1. So equal to G, that is what it actually is saying, and in Pythagorean notation it becomes this. So it preserves the metric delta ij. So we would have written O Ji delta ij O so sorry, ik. So j has to try to this, so kj, okl, right? I wrote, so I meant to write the transpose of oij, so it is oji, but it is the this index which was actually here tied to this, so j tries, so it should be jk, I am sorry, jk okl equal to delta il. So that is another way of thinking about what the O matrices have to do. Okay. And similarly we can write out for the complex matrices. So once we write like this, we can write out the Minkowski case. The metric is denoted eta and is equal to 1 minus 1 minus 1 minus 1. Okay. This has now become the standard choice in advanced physics. So in the old days they were taking minus 1 here and taking plus 1s here, because it will return the usual Pythagorean thing for the 3D. But over time this has become preferred. So this is preferred because the energy will have a positive sign because it's the 0th component. Okay, that's the difference. But this has become the standard choice. And in this case, so this generalizes the Gaussian restriction of positive definiteness, but now it is indefinite, that is the only difference. And then the requirement is so this is another way of writing out the Minkowski inner product. This group, I should check here some notation here because the placement of indices is somewhat important. I will correct it next time. But this group we call SO3, 1. This means 3 of the signs in the metric preserved by this group are opposite to the 4th sign. So there is a old theorem called Sylvester's theorem, which says that the number of signs of the eigenvalues remain the same under transformations. So regardless of what basis you choose, you will have 3 of the eigenvalues negative and 1 eigenvalue positive, and or 3 positive and 1 negative, either way is fine, but they are opposite, that is all it says. So multiplying the eta overall by one sign doesn't change this relation. And there were many versions in operation. People actually at one point used to write I, the imaginary unit, and plus 1 plus 1 plus 1. Plus 1 plus 1 plus 1, so that it gives the usual length squared, and that I saves you the embarrassment of admitting that there is a minus sign, that actually it is indefinite. So it looks like Pythagorean. But eventually people stopped being afraid of minus sign and started writing the minus sign explicitly in the metric. So in fact, Pauli has an article written in 1920 where he introduced the ICT notation to avoid writing a minus sign. But eventually people realized that actually the structure of the group changes because of the one sign opposite. The representation theory changes. Okay, so I think we will stop here. What was I going to say? It was about some geometric thing, right? So we will do it next time.